Example 1.1. The current source and voltage drop across the circuit are plotted. Determine the power and energy absorbed by the element, and then sketch the curves afterwards. So if we want to determine the power, then this is what this means here. That the power is a function of time, and it's going to be the current source times the voltage. And the energy, written as W of t, is then going to be the integral of the power function relative to their interval right here. So the first thing that we have to do here is that we need to parameterize the current and voltage curves. So let's start with the first one. We're going to do the current versus time curve. So if I look at the curve, what am I seeing? I have this guy right here. Now, when I'm looking at this thing, you can see that the first part of that thing is a constant. The second part is a linear line. So that means here, so if I look at the interval between 0, t, and 1 second, that tells me that this guy should be a constant, which is plus 1 amp. But if I look at between 1 and 2, that changes. So between 1 and 2 seconds, you see that I have a linear line. So if I have a linear line, that tells me that this function will have some slope and some intercept. So if I look at this curve, this is what I'm going to be focusing on right here. So in order to calculate the slope and the intercept, I'm going to need 2 points. So I'm going to pick 2 points on this curve. One is right here, which will be at 1 second, it's 1 amp. And at 2 seconds, it's 0 amps at this point right there. So let's look at that. So if I look at the slope, which is m, that means I can calculate this by looking at the slope between these 2 points here. So if I put in my numbers, I get a -1 amp per second slope. So I now know what my slope is. Now to get the intercept, B, what I do here is that I pick 1 point along this line. So what we do know here is that the easiest point is to pick 0, 2. So let's look at that. So if I look at the line equation at t equal to 2 seconds, I know that has to have a slope of -1 plus the intercept. But then at 2 seconds, this tells me that this has to be 1 times 2 plus b, and that guy is going to be 0. So this automatically tells us that the slope b is then going to be +2 amps. So now I have my parameterized current. So if I look at my current here, I then see that I have IS of t. And what I'm going to have here is that I'm going to have 1 amp between 0 and 1 second, and then I'm going to have minus t plus b for between 1 and 2 seconds. So now I have my current. So now I'm going to do the exact same thing for the voltage here. So if I look for the voltage, I'm going to see here, following the same process as before, that means I got to break down my curve, pick points, because I'm going to have linear lines. So here we go. So this is 2. And this is going to be the V of t versus t curve. So if I look at this guy, I know that this guy is my curve. So you can see that I have 2 linear lines. So I have 3 regions between 0 and half a second, and 1, and then 1 to 2 seconds. So let's go do that. So when I look at this curve, if I'm going to parameterize these gains, I need to pick my points. So here I go. I have a point right here, which is 0, 0. I have an obvious point here of 3.5 seconds. And then this guy is going to be 0 at 1 second. So when I look at my curve, you could see here that I'm going to break it up into 3 pieces. You could see here that I'm going to have some M1t plus B1. I'm going to have M2t plus B2. And that is for the interval of half a second, between 0 and half a second. And then from half a second to 1 second. And then you could see that the voltage goes to 0 for t greater than 1 second. Now, when I look at this thing, there's a couple of things that I could say. Immediately, we can look at this thing and we could say this. This slope is 0. You can see that it starts at the origin. And if you also look at these slopes, you can see here is that they have opposite slopes. So that means that M2 is going to be minus M1. So I can refine these equations just a bit more. So let's calculate the first region. So between this and half a second, what I'm seeing here is that I need the slope of which I'm calling M1. And that, so I'm going to pick my 2 points off of the first line here, the positive slope line. And so this is going to give me 3 minus 0, half a second minus 0. So this gives me 6 volts per second for M1. And we already said here that B1 is equal to 0. So you could see immediately that the voltage between 0 and half a second is then going to read 6t plus 0. So now I have my curve. So I got my first line. Now let's go look at the second line. So we already said that if I look at the slope here, that this slope M2 should be minus 1. So we know that this guy is minus 6 volts per second. So I now know what that slope is. So now I got to get the intercept. What we did before is that we had to pick 1 point along this line to get B2. So I'm going to pick the easiest thing. So I'm going to pick point 0, 1. Now, let's look at our equation. So our equation, I need to be at 1 second. So this will be a t at 1 second. Now we know that the slope is minus 6t plus b2. So now if I put in my times here, this is going to be 6 times 1. So I'm going to get minus 6 plus b2. And then we see that the voltage is 0 at that point. So that has to be 0. So this immediately tells us that B2 is then going to be positive 6 volts. So if I now look at this curve, I know that for half a second to 1 second, I'm going to have minus 6t plus 6. So now I have my parameterized curve, because we know that from 1 to 2 seconds, it's 0. So let's write this out then. So now, if I look at my voltage as a function of time, you can see here it's going to be 6t minus 6t plus 6, and then 0. And this is for these time intervals. So now I can solve the problem. So what I'm going to do here is that I'm going to set up a table. I'm going to set up a table for organization. So here I go. So I need my times. So my times are this. And then I need 1 to 2 seconds, and then for t greater than 2. Okay, so this is my time. Now, so now I'm just going to start to put in my parameters now. I know that this is my current. And when we looked at our current, we saw that it was constant in the beginning. And then it had a linear line, and then it turned off. When I look at my voltage, we saw here that it was 6t minus 6t plus 6, and then it went to 0 and 0. So now if I look at the power, which is I times V, then you can see I just got to multiply these together. So this will give me 6t minus 6t plus 6, 0, 0. So to get the energy, we have to integrate the power as a function of time. So we have the powers now. So now I have to calculate the energy deposited into the element. So I'll calculate these one at a time. So if I look at my first work, that's between 0 and half a second. So that means then I have to integrate the power. So if I integrate the power, it's going from 0 to t, and the power here is 6t dt. And if I compute this, this is going to be 3t squared minus 0. So it's 3t squared. So here I go. There's my power. Now, when I look at, because this is not continuous, it's piecewise continuous, I'm going to have to break up my integral to go from 0 less than t all the way to 1 second. So here I go. So I got to go from, that's the work of 1 at t equal to half a second, plus from half a second all the way to t of my next one here, which should be minus 6t plus 6, then I have to integrate that. So if I compute that, what do I see? The first thing that I see here is that I know that the power is 3t squared. So if I do that for half a second, I'm going to get 3/4 for that term. Now, if I integrate the first term, I'm going to get minus. So I'm going to integrate 6t, which will give me 3t, but I have a minus sign. So this is going to be 3t squared. And that goes from half a second to t. And then my second term is going to be 6t, which goes from half a second to t. So if I put in my numbers, this is what I'm going to get. I'm going to get finally that I'm going to get minus 3t squared plus 6t minus 1.5. So my power is then going to be minus 3t squared plus 6t, drop the t, that's going to be minus 1.5. So now if you look here, there's no more power from 1 to 2, or for greater than 2 here. So that means this energy has to be constant now. The energy of the system cannot change. So if I look at the interval, from 1 to 2, the only contribution that we have then has to be the work at 2 at t equal to 1, because that's the last time energy was flowing into that element. So if you compute that number, you could see here that you're going to get a value of what? You're going to get a value of minus 3 times 1 squared plus 6 times 1 minus 1.5, and that gives me plus 1.5 joules. So therefore, this is 1.5 joules, and because the power here is 0, that energy cannot change again. So this also has to be the same thing here for t greater than 2, and that will be plus 1.5 joules. So now if I go and I plot these curves, here's what I'm going to do. So now if I plot the power and energy, I have the following thing. So I look at my curves, and I'm going to go 1, 2, 3, 4. And I'm going to set my time at 0, half a second here, and this is 1. So note that the voltage looks just like the power. So it's the exact same curve as up here. It looks exactly the same. The only thing that's different is that it has different units. So then I'm going to see here is that this guy's going to do what? It's going to climb up to here. It's going to have a peak power. And then the power starts to decrease, but it's still adding power to the circuit. So in this case, this is going to be 3 watts, and this is the power of T. And then afterwards, you could see here that this guy is 0. So if I look at this thing, this is the power right here. Now I could say the same thing about the energy now. So if I look at the energy, this should be different. So I'm going to go again, half a second. I'm going to go to 1, and then, it'll go on to 2 here. But what do we actually see here? We see that the maximum energy is 1.5 joules. So if I look at this thing, I'm going to go 1, 2, 3. I'm going to come up to here. And this is going to be 1.5 joules. So I know that when I get to 1 second, that has to be the maximum energy. So at this point, I should have a constant line. So let's look at this thing. So if I look at this guy, it's got to look something like this. So the beginning goes as quadratic as 3t squared. So what you're going to see here is that it's going to come something like this. And then I have a negative quadratic that has to attach to that point smoothly. And it's going to look like this. So you could see here is that this is the 2 intervals that you're looking at here. And so this guy is the energy curve. And again, this line right here shows that the power supply stops supplying any additional energy.